What if I told you that the Hubble telescope has just unveiled mind-blowing secrets about Betelgeuse? Well, Betelgeuse seems to have spilled its secrets, and astronomers are buzzing with excitement. What kind of unseen forces are at play, shaping the destiny of this colossal celestial body? Could this revelation challenge everything we thought we knew about the life cycle of stars? Join me as we unravel the cosmic enigma together, going deep into the latest data from the Hubble telescope. With that said, let's get started. Betelgeuse had a bit of a mood swing recently, and NASA's Hubble Space Telescope has just revealed what happened. Betelgeuse is so huge that if it took the sun's spot in our solar system, its outer surface would reach Jupiter. Now, this star has been doing its thing for ages, with its nuclear fusion processes going on. But then, in October 2019, something strange started happening. Betelgeuse went dim. Astronomers were scratching their heads trying to figure out what was going on. Was Betelgeuse just having a bad star day? Or was there something more to this dimming drama? Fast forward to mid-February 2020, and Betelgeuse's brightness had dropped by more than 3 times. Thanks to the Hubble Space Telescope, we've got some answers. It turns out that Betelgeuse's dimming was a result of a massive dust cloud formed by hot material being ejected into space. Betelgeuse decided to spice things up by unleashing super-hot plasma, creating a dust cloud that played hide-and-seek with its starlight. Now you might wonder, how did Hubble figure this out? Well, it's all about the ultraviolet light. Hubble's been keeping an eye on Betelgeuse since January 2019, taking some stellar snapshots. The telescope's ultraviolet sensitivity allowed researchers to peek into the layers above Betelgeuse's surface where things were heating up, literally. Hubble's ultraviolet observations in September, October, and November 2019 caught a glimpse of dense, heated material on the move. This material traveled outward, reaching millions of kilometers from the star. As it cooled down, it formed a dust cloud. Lead researcher Andrea Dupree explains, "We could see the effect of a dense, hot region in the southeast part of the star moving outward." About a month later, Betelgeuse's southern hemisphere dimmed like the lights going down in a theater. The team suspects that the dust cloud causing this dimming was a result of the outflow Hubble detected. Now, you might be wondering, why did Betelgeuse throw this stardust in the first place? Well, that's still a bit of a mystery. Dupree suggests it might have been assisted by Betelgeuse's pulsation cycle. The Hubble observations also revealed that Betelgeuse's pulsation cycle was doing its thing as usual during this dimming event. Klaus Strassmayer, using the Stellar Activity Telescope, measured changes in the velocity of gas on Betelgeuse's surface as it pulsated. The pulsations might have helped propel the plasma outflow through the atmosphere. Now, here's where it gets even more intriguing. Some astronomers think this sudden dimming might be a prelude to Betelgeuse's death. The red supergiant is destined to go out in a spectacular supernova blast, and this dimming event could be the pre-show. Betelgeuse is about 725 light-years away, so this dimming event happened around the year 1300, and we're just seeing it now. Dupree and her cosmic crew are gearing up for another rendezvous with Betelgeuse using Hubble in late August or early September. Right now, Betelgeuse is playing hide-and-seek with the sun in the daytime sky, making it a bit tricky for Hubble observations. Who knew stars had such a flair for the dramatic? Keep your telescopes ready, because the cosmic drama continues, and Betelgeuse might just have a few more surprises up its sleeve. It's quite well known that stars, including Betelgeuse, rotate, but Betelgeuse seems to be spinning faster than what scientists had predicted. Now, why is that a big deal? Well, it's because stars like Betelgeuse, as they evolve, should actually be slowing down their rotation. The current theory suggests that red giants, which Betelgeuse once was, rotate at a speed of about 1 kilometer per second. When they evolve into red supergiants, like Betelgeuse now is, the rotation is expected to be a bit less than 0.1 kilometer per second. But here's where it gets interesting. Recent observations have shown that not only Betelgeuse, but many other giant stars are spinning faster than the predicted values. Now, let's focus on Betelgeuse for a moment. Scientists were able to measure its rotational velocity using the ALMA, and guess what they found? Betelgeuse is rotating at a speed of around 5.47 kilometers per second. That's way faster than the expected speed for a red supergiant. But why does this matter? Well, scientists are trying to figure out the reasons behind Betelgeuse's unexpected spin. One leading theory suggests that Betelgeuse might have had a merger with another star, a low-mass companion star. It's not as uncommon as you might think. About 1/3 of red supergiants experience a stellar merger before reaching the end of their lives. Scientists are also considering the possibility of these stars merging with planetary systems. It's like you're spinning with your arms out and suddenly someone hands you a basketball. Your spin changes, right? That's the idea scientists are exploring when it comes to red giants. But there's a possibility that the observations of Betelgeuse's rotation could be wrong. The signals picked up by astronomers could be coming from the turbulent surface of the star rather than its actual rotation. So, to really get to the bottom of this mystery, scientists had to develop new techniques. They dove into the world of 3D radiation hydrodynamic simulations, a fancy way of saying they created computer models mimicking red supergiants with properties similar to Betelgeuse. It's like creating a virtual Betelgeuse on a computer screen to see how it behaves. And what did they find? Well, the team concluded that to be absolutely sure about Betelgeuse and other red supergiants spinning rapidly, we need better technology. We need higher resolution observations than our current technology can reliably provide. By the way, do you know that Betelgeuse is a fast-moving red supergiant with a stellar wind, and this wind creates a bow shock? A kind of cosmic wave as it pushes against the surrounding space. Some astronomers discovered something unexpected, a dense and almost static shell, 3 times closer to Betelgeuse than the bow shock. What's even more mind-boggling is that this shell has been slowed down by some external force. The usual explanation for such structures involves the interaction of the stellar wind with the interstellar medium. But in this case, it seems like that explanation just doesn't cut it. Some brilliant minds came up with a model that explains this static shell without throwing the bow shock, and it involves Betelgeuse's wind getting a makeover through photoionization. External sources are bombarding Betelgeuse's wind with radiation, causing it to transform into a photoionized wind. Now, what's so special about this photoionized wind? Well, it's got some pressure up its sleeves. This pressure creates a standing shock in the neutral part of the wind, forming that almost motionless shell. But why stop there? Let's think about other red supergiants in the galactic neighborhood. Betelgeuse might be stealing the spotlight, but its fellow red supergiants should have even more massive shells. These are called photoionization-confined shells. Photoionization-confined shells are a phenomenon that occurs when a star emits a strong wind of gas and dust, and this wind is exposed to radiation from other sources, such as nearby stars or the interstellar medium. The radiation ionizes the wind, meaning it strips away some of the electrons from the atoms, creating a plasma. This plasma exerts pressure on the neutral part of the wind, creating a shock wave that slows down and compresses the gas. The result is a dense and almost static shell of gas around the star, which can trap a significant amount of mass and affect the star's evolution and eventual explosion as a supernova. This phenomenon has been observed in some red supergiant stars, such as Betelgeuse. These photoionization-confined shells are like cosmic treasure chests, trapping up to 35% of all the mass lost during the red supergiant phase. Now let's break it down. Red supergiants, including Betelgeuse, go through a phase where they shed their outer layers. The photoionization-confined shell plays the role of the ultimate cosmic collector, keeping all that lost mass close to the star until the day it decides to go out with a bang. After the red supergiant phase, these massive shells play a starring role in the supernova light show. The trapped gas in the photoionization-confined shell dramatically affects the supernova light curve, giving us a natural explanation for those supernovae that show signs of circumstellar interaction. Now, don't deny it. We've been waiting for it to explode like a cosmic firework, but it seems like Betelgeuse is playing hard to get. Most experts are telling us not to wait for it, but there's this team of astronomers who still believe it might happen sooner than we think. According to the astrophysicists, right now, deep in the heart of Betelgeuse, helium atoms are fusing into carbon atoms. This whole process takes thousands of years, and Betelgeuse has some serious steps to go through before its grand finale. But Hideyuki Sayo and his astronomy squad from Tohoku University are suggesting something different in their recent study. They claim that Betelgeuse might be almost done burning carbon, and after that, it could be just a few decades before it runs through oxygen and silicon. How did they come up with this theory? Well, the answer is its pulsations, to be exact. Betelgeuse has this rhythmic cycle. One cycle takes about 420 days, during which the star expands and contracts. There are also shorter cycles, kind of like subbeats, where different layers of the star pulse in opposite directions. Now, here's Sayo, and the team has come. They've noticed an even longer cycle of about 2,200 days, a slow undulation, as another group of astronomers describes it. Most thought this was caused by external factors, like nearby space dust. But no, Sayo and the team say this long cycle is Betelgeuse's main pulsation period. If they're right, it means Betelgeuse is way bigger than we thought, like 1,300 to 1,400 times the size of our Sun. And if size does matter, Betelgeuse might be in its late stage of carbon burning, setting the stage for a spectacular cosmic finale in the next few decades. But not everyone is buying this. Harvard's Andrea Dupree and another group led by Laszlo Molnar argue that Sayo and his team might be reaching a bit too far. They say telescopes have been keeping a close eye on Betelgeuse in different light wavelengths, and all the data they've collected points to Betelgeuse being smaller than what Sayo suggests. According to them, Betelgeuse is maxed out at 1,100 times the size of our Sun, not enough for that super long 200-day pulsation cycle. So, who do we believe? Are we on the brink of witnessing a cosmic spectacle, or is Betelgeuse just playing hard to get, teasing us with its light show? I can almost hear you asking, why does it even matter? Well, it matters because Betelgeuse going supernova is like winning the jackpot. We're talking about an explosion so powerful that it will outshine entire galaxies. But if Betelgeuse is as close as we think it is in size, then this jackpot might be one we'll have to wait a bit longer to hit. On one hand, Sayo and his team are saying, get ready for the show. On the other hand, Dupree and Molnar are like, it's not happening anytime soon. So, what's the takeaway here? If Betelgeuse is indeed the giant Sayo and team propose, then we might be in for a stellar spectacle sooner than later. But if it's more on the petite side, as Dupree and Molnar argue, then we might be in for a longer wait. And there's a lot at stake here. Betelgeuse going supernova is not just a show for us to enjoy. It's a cosmic event that will teach us more about the life and death of stars. Betelgeuse continues to flicker in the night sky, keeping us on our toes. The astronomers are locked in a debate, analyzing data and tweaking models to understand this cosmic enigma better. But could Betelgeuse pose a danger to Earth? Should we be worried? If a supernova were to happen within a few tens of light years from us, it wouldn't be a pleasant cosmic event. A supernova can become as luminous as an entire galaxy, and if it's close enough, we'd be bathing in all sorts of radiation. This is not a situation we'd want to be in. The last time we witnessed a supernova in our galaxy was back in 1604. However, in 1987, one lit up in the Large Cloud of Magellan, a distant neighbor about 169,000 light-years away. Thankfully, that one didn't pose a risk. So, what's the danger zone around a typical supernova? My rough estimate is around 100 light-years, but I'm not an astrophysicist. Still, it seems safe to say that Betelgeuse is comfortably out of our danger range. But there are other stars out there that could be potential troublemakers. Take Eta Carinae, for instance. It's massive and unstable, and who knows when it might decide to go supernova. The catch is, it's about 8,000 light-years away, so no worries for us. Then there's Rho Cassiopeiae, a yellow hypergiant. It's shining brightly, and it's a bit of a mystery. But guess what? It's a whopping 9,000 light-years away, well beyond our cosmic danger bubble. I even did a little catalog search for potential supernova candidates within 100 light-years, and I couldn't find any. We're in the clear from nearby exploding stars, it seems. Now, Betelgeuse does seem to be the closest potential troublemaker. It's closer than Eta Carinae or Rho Cassiopeiae. If it decides to go supernova, we'll get a front-row seat to a spectacular cosmic event. Imagine the night sky without Betelgeuse. Orion, the celestial hunter, would lose a shoulder. I don't know about you, but on every clear winter night, I take a peek at Orion to make sure Betelgeuse is still shining bright. In 2009, a group of scientists led by P. Curvella did deep research on Betelgeuse, and I recently stumbled upon their scientific paper published in Astronomy and Astrophysics, which shed light on some fascinating aspects of Betelgeuse. The scientists used a powerful tool called the VLT-NACO instrument to observe Betelgeuse in the near-infrared spectrum. This instrument, equipped with adaptive optics spectroimaging capabilities, allowed them to get a closer look at the star and uncover some intriguing phenomena. One of the remarkable findings in the paper was the detection of an asymmetric envelope around Betelgeuse. There's a bright plume extending in the southwestern quadrant, reaching up to 6 times the photospheric radius of the star. Now, this plume could be caused by 2 things: either a convective hotspot on the photosphere or the rotation of the star itself. Adding to the spectacle, the paper confirmed the presence of a chromospheric hotspot in the same region. This hotspot was previously observed in the ultraviolet, highlighting the multispectral nature of Betelgeuse's light. But why is this significant? Well, it provides a glimpse into the star's dynamic behavior. The scientists didn't stop there. They went on to analyze the spectral energy distribution of both the photosphere and the circumstellar envelope of Betelgeuse. Think of it as dissecting the star's light to understand its composition. In this process, they identified a strong absorption feature around 1.1 to 1.3 microns. So, what could be causing this absorption? The scientists suspect it might be due to CN molecules. Now, CN molecules might sound complex, but they're essentially cyanide, a compound composed of carbon and nitrogen. Isn't it intriguing to think that such common elements on Earth are found in the outer reaches of a distant star? The paper also raised the possibility of water and dust in Betelgeuse's close environment. Water, a fundamental component of life on Earth, might be lurking in the cosmic vicinity of this massive star. Dust, which may seem mundane to us, plays a crucial role in the cosmos, shaping the environment around stars. See another scientific article, focusing on imaging the surface of Betelgeuse in the H-band, provided even more insights. Using interferometric observations from the IOTA instrument, the authors revealed the presence of 2 bright spots on Betelgeuse's surface. What do you think these bright spots could be? Convective cells, where material moves in a circular manner, or hotspots, regions hotter than their surroundings. In their quest for understanding Betelgeuse, the authors went beyond just spotting these bright features. They measured the limb-darkened diameter and the effective temperature of the star. Limb-darkened diameter is essentially the apparent size of the star when viewed from a distance. Effective temperature gives us an idea of how hot or cold the star is. But why is measuring these parameters important? Well, it helps us paint a more detailed picture of Betelgeuse's character in the vast cosmic landscape. Interestingly, the authors also noticed a fully resolved environment around Betelgeuse, possibly due to scattered light from a dust shell. To make sense of their observations, the authors employed different models like parametric limb darkening models, a Marx model of the photosphere, and a radiative transfer model of the dust shell. A radiative transfer model is a way of calculating how light changes as it passes through a medium, such as the atmosphere of a planet or a star. It takes into account how light can be absorbed, scattered, or emitted by the particles in the medium, and how this affects the intensity, color, and polarization of the light. The radiative transfer model is useful for understanding the properties of astronomical objects from their spectra, such as their temperature, composition, and structure. These models are like different lenses through which we can view and understand Betelgeuse. Understanding the dynamics of Betelgeuse provides valuable insights into the life cycle of stars, the elements they produce, and the impact they have on the cosmos. As we peer into the depths of space and unravel the mysteries of Betelgeuse, we are essentially unraveling the story of our own cosmic origins. The elements forged in the fiery furnace of stars like Betelgeuse are the same elements that make up our bodies and the world around us. It's a cosmic connection that goes beyond the vast expanse of space. The universe never fails to surprise us. From mysterious dimming events to unexpected spins and pulsations, Betelgeuse continues to captivate our imagination. Now, it's time for you to become part of the narrative. Grab your telescopes, keep your eyes on the night sky, and join us in the quest to unravel the secrets of Betelgeuse and the cosmos. Subscribe for more updates, hit the like button if the wonders of the universe leave you in awe, and share your thoughts in the comments below. Together, let's explore the cosmos and witness the spectacular events that stars like Betelgeuse have in store for us. Until next time, may your nights be filled with celestial wonders.